Hi, my name is Dear Tiagi, and in this video, I'll be going over TNB frames plus curvature and torsion for Calculus 3 students. So to start, why do we use TNB frames, and what are they useful for? So when we're looking at a space curve, we often look at the space curve from the origin, but the issue is this isn't always useful. So the idea with the TNB frame is instead of viewing this curve from the origin, we're going to be looking at it from the particle moving on the curve itself. So for example, let's say we have a space curve in an XYZ plane. So we have an XYZ plane, and we have some kind of space curve, like so, right? When we're looking at this curve, normally we'd start at the origin, and we have our I vector, our J vector, and our K vector, and we'd be observing the movement of the curve and define the curve in terms of I, J, and K. But the idea is sometimes that isn't useful, and so the idea with TNB is instead of defining it as I, J, and K, we move this and we rotate it such that we have a particle in space, or a point in space, where we have a defined t unit vector, a n unit vector, and a b unit vector. So instead of viewing this space curve from the origin, we're viewing it from a particle moving along that curve in space at a single point. So TNB stands for tangent, normal, binormal. In the first one, tangent, the way we calculate it, right? So again, these are unit vectors. So we want to find the vector with length 1. So basically just the direction. And so the tangent tells us the direction a particle is heading. And I actually have a little plane here. And the way to think about it is the tangent vector is telling us the direction or where the nose of the particle is pointing. So for example, let's say we're on the space curve and we have this plane, right? So the tangent vector is going to be telling us which direction it's heading from the nose, okay? And the way we derive the tangent vector, it's given symbol uppercase T. So the tangent vector is equal to r prime of t over the magnitude of r prime of t. So we're just looking for the unit vector. In terms of s, if we parameterize that in terms of s, t prime of s, the tangent vector with respect to arc length, is equal to r prime of s. Okay. Next, for the n, we have normal. And just for idea, tangent could be similar to sort of like an x, or sorry, I hat. You can kind of think like that. And then normal could be think of it as like a j hat, sort of. And so normal is given the formula of t prime of t over the magnitude of t prime of t. So the normal vector tells us which direction the particle is turning. So if we look at our plane, if the plane was going to be turning, right, when planes turn, they kind of do something like this, right, and they turn like that. And so when we're looking at a plane, the normal vector would be this kind of tail, right here, this tail here. And so when we're turning, right, the tail is going to be pointing this way, which says that it's plane, right, so it's pointing this way, which means our plane is turning left, right? So the normal vector tells us which direction it's turning. So I should probably write that direction turning versus the tangent vector, which is telling us the direction it's heading. And so one thing you might notice is that the normal vector is equal to basically just the derivative of the tangent vector. And the reason why this is true is because there's a statement that if we have a, if we take r prime of t, sorry, r of t, and dot it with r of t, and it equals a constant, then r of t dotted with r prime of t is equal to 0. And the reason why this is true is because proofs, but also the idea, the statement, a generalized statement, is that every vector with constant length is orthogonal to its tangent vector. So in other words, if you have a vector with constant length, it's going to be tangent to its direction or to its derivative vector. And the final thing is binormal, which you might have guessed from our orientation is going to be equal to the cross product of our t vector and our normal vector. And if we want to find it in terms of r, we can say that it equals, right, because this is r prime of t, so r prime of t cross r double prime of t, right, because that's also just equal r double prime of t over magnitude of r double prime of t, right, over the magnitude of r prime of t cross r double prime of t. So in terms of what this tells us, the binormal tells us the direction it's twisting. So if I bring back my plane, the binormal would be kind of like the wings, and it would tell me what direction I'm twisting. So it doesn't matter which wing, the wing would just tell us which direction it's twisting. But for example, let's say we're twisting this way, right? Our binormal vector, so our normal is this way. Our binormal would be this way, right? Because the normals, sorry, the tangents this way, normal's this way, so orthogonal to this and this would be this way. So our binormal is this way, pointing along the wing, and it's telling us which direction it's twisting, right? So it's twisting this way, which is why you're going to see it like kind of rotate like that. Okay, and so that's the TNB frame. Next, let's go over curvature and torsion, which is a concept that goes pretty hand in hand with TNB frames. So curvature tells us, gives us a measure for the failure for a curve to be a line. So the more curvy we have a space curve to be, the more curvature we have. And the symbol for curvature is given the symbol kappa, or which just looks like a K. So it's more curvy, it's increasing kappa. And the formula is that kappa, or curvature, is equal to the magnitude of t prime of s. So arc length, or sorry, tangent, the derivative of tangent parametrized by arc length. Or in other words, k is equal to dt over ds, the magnitude of that. Okay? And another formula we have for this in terms of not dt, in terms of dr, is that t prime of t over r prime of t, and it's equal to this. So why is it equal to this? Why is this equal to this? The reason why is we imagine, right, k is equal to dt over, let's say, dt times dt over ds. This is the same thing as this, right? Because the dt's cancel out, we get dt over ds. That's the same thing. And we know that dt over dt, right? So if we can rewrite this as dt over dt over ds over dt, right? Because this is going to flip because we're dividing. So dt over dt is going to give us t prime of t. ds over dt is going to give us r prime of t, which is how we derive this. And then if we consider what t prime of t really means, and we consider what r prime of t is, right? We also get the fact that r prime cross r double prime divided by r prime cubed is also equal to the curvature. And this is fully in terms of r, which might be more useful than in terms of t and r. And finally, we have torsion, which is pretty similar to curvature. And torsion tells us how much a line fails to be contained in a plane. So the more it's not in one plane, the more torsion, or what we say tau, the symbol for tau, or torsion, it has. So tau is equal to, or torsion is equal to the negative derivative of the binormal with respect to arc length times the normal. It's also equal to, if you consider what this actually means, it's equal to r prime cross r double prime times r triple prime over r prime cross r double prime squared. And just go over a quick reason why this is true. If we consider that dB over ds is equal to the derivative of the cross of tangent times the normal with respect to ds, we know that this equals, right, by product rule, dt over ds cross n plus dn cross ds, or dn over ds cross t. And we know that dt over ds right? We just said over here dt over ds equals some value k. The magnitude equals k, or curvature. Therefore, dt over ds, just the derivative, the magnitude, or with magnitude, would be k n, right? Because we're multiplying by n because k is just the magnitude cross n, right? We know that when we cross two of the same vectors, we're going to have a theta equaling 0. Sine of theta, therefore, is equal to 0. Therefore, this is 0, kn cross n, plus dn ds cross t. And so the idea here is we know that the function, right? So we know that dn ds cross t is equal to dv over ds. We know that it's going to be, this dv ds is going to be perpendicular to t, right, because we're crossing it. And one thing we also know is it's going to be perpendicular to the binormal. And the reason why is because, again, what I said before, when we take the derivative of a vector with constant length, that derivative is going to be perpendicular or orthogonal to that original vector. So it's going to be also perpendicular to b. And then therefore, we can consider dv ds is going to equal some value t, so right, some scalar multiple t times n. And again, the reason why is because we know it's perpendicular to t, it's perpendicular to b. Therefore, it's going to be parallel to n. And so if it's parallel to n, that means it's going to equal some scalar multiple times n, which is what I said here, t times n. And if we move n to the other side, we get a tau, or torsion, is equal to n times dv over ds. And we just have the negative in front of here just for kind of, that's how we define it. We define it with negative. But it really doesn't matter. We can add a negative. Because again, t is just a random constant that represents torsion. And yeah, that's TNB frames plus curvature and torsion. Thank you all for watching, and I'll see you guys all tomorrow. Bye.